Okay, this is Advent of Code, day 17 in OCaml in 3, 2, 1, go. Day 17, Pyroclastic Flow. Your handheld device has located an alternative exit from the cave for you and the elephants. The ground is rumbling almost continuously now, but the strange valves bought you some time. It's definitely getting warmer in here, though. The tunnels eventually open into a very tall, narrow chamber. Large, oddly shaped rocks are falling into the chamber from above, presumably due to all the rumbling. If you can't work out where the rocks will fall next, you might get crushed. 5 types of rocks have the following peculiar shapes. Okay, so we are playing Tetris. First the minus, then the plus, and so on. Minus, plus, right angle, okay. In jet patterns, left means a push to the left, while right means a push to the right. Push a falling rock, right, then right, then right, then left, then left. Okay. All right, we are literally implementing Tetris. Tall vertical chamber is exactly 7 units wide. Each rock appears so that its left edge is 2 units away from the left wall, and its bottom edge is 3 units above the highest rock in the room. After a rock appears, it alternates between being pushed by a jet of hot gas 1 unit in the direction indicated by this next symbol in the jet pattern, and then falling 1 unit down. If any movement would cause any part of the rock to move into the walls, floor, or a stopped rock, the movement instead does not occur. If a downward movement would have caused a falling rock to move into the floor or an already fallen rock, the falling rock stops where it is, having landed on something, and a new rock immediately begins falling. All right, so it's pushed by gas and then falls. Got it. To prove to the elephants your simulation is accurate, they want to know how tall the tower will get after 2022 rocks have stopped, but before the 23rd rock begins falling. Okay, so all of these repeat. All right, so we have holy cow. 10,091. Okay, so string dot strip s string dot to list module push list.map fun ch match function match, or no, push dot left, push dot right. Okay. Oh. Fail with unknown character. And so let's see. Do I have stack in here? I don't know why these pages take so long to load. Let's see. Module. Board. Type T equals so we're gonna have a list, a rows of array.t's actually, this is what I will do, because I know that it's 2022 array.t. Cool. Let's do mutable max height, max rock equals int yeah, but create num rocks equals rows equals array. I don't want, do I want a container? Create init. Okay. Let max rock height equals 4. Actually, yeah, 4. Let rows equals num rocks times 4 plus 3 plus 4. Let max height equals in, let rows equals width is int. Init max height fun array dot create with false. When in rows columns oh, that is not what I wanted to do. Set text width equals rows with max rock. All right, let board equals board dot create with 7 num rocks equals in. What did I call this? Push. Pushes. I think there's sequence. Whatever. Type sequence equals what is the type of S? Equals pushes T-list index int mutable. create sequence pushes equals pushes index equals 0. Let next s equals array. Array dot of list pushes. If index equals array dot length, then equals 0. Let n equal s dot pushes in push dot create seek print push dot next pushes in 10 do push dot t. With int numrocks int okay. Max rock height What's up, Angered Gecko? So I want right, 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 left, right, 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 left, right, right. Right, 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 left, right, 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 left, right, right. Perfect. All right, I have my pushes sequence. Module loop seek type at equals elms a t array Elms. Cool. Loop seek. Let's see. Type. Let line equals 0, 0, 1, 0, 2, 0, 3, 0. Let plus equals 1, 0, 0, 1, 1, 1, 1, 2, 1, 2, sorry, this is 2, 1, 1, 2. L equals 0, 0, 1, 0, 2, 0. 2, 1, 2, 2. Whatever. These don't really need good names. 0, 0, 0, 1, 0, 2, 0, 3. And box equals 1, 0, 0, 1, 1, 1. Let box equals line plus L bar box. Wait, this. Oh, that's just, okay, there we go. All right, so that's pushes, and then let rocks equals loop seek dot create rocks in. Okay, and then how tall the tower will be. Okay. For equals 1 to 20. Let num rocks equals 2022 in oops, rocks do, done. Print oh, that's fine. So it starts off 3 above. So it should be 0, 1, 2, 3. So it should be +3. Let's see. First clear row. Board. First clear row. Rock equals loop seek dot next rocks in board dot drop rock board rock pushes. Let drop rock T rock pushes equals rock equals init place init rock T rock in let and then loop while let fell equals ref true in while fell do done. Let ref dot try push T rock ref rock equals try push rock, and then fell equals try drop T rock. Okay, let init rock let try drop T rock equals true. Let try push T rock equals rock. Rock equals all right, so we rock list dot map rock f x y x plus 2, y plus first clear row. Yeah, probably. Let offset equals 3. Okay, so okay. Try push. Let update chords x dx rock dx dy equals. Array dot map rock dx dy update chords rock 2 t first clear row plus offset. Try push. Let push dx equals O. Try push loop seek dot next. Pushes push match push with left -1 right 1 in let pushed rock equal update chords rock dx 0 dx dy 0 in if let any overlaps t rock equals false. If any overlaps t pushed rock, then pushed rock, else rock. Equals array dot any collisions exists rock f x y t dot rows let place rock array dot iter rock f Oh, I can do this the other way with that will have poor cache locality though. T dot rows dot y x OCaml array. Okay, perfect. If any collisions, try drop. Let dropped rock fell. Did it fall equals try drop t rock in rock maybe dropped maybe dropped rock fell did it fall yeah place rock t rock any collisions array dot try drop if array dot exists rock f fun y zero return then false then rock false else let dropped rock any collisions then rock false dropped rock true. Rocks. This is a int array list. Oh, there we go. Nope. Place rock, and then array.iter rock f fun y. Oh. I need to do if in bounds. Let in bounds t rock equals not array.exists rock f x y. Or x t dot width or y is less than 0. If in bounds t rock and if not in bounds t rock or iter if y is greater than equal t dot max rock height then t dot max rock height y. Update max rock height t rock. Update max rock height t. Ah, that's why. First clear row. Clear row. Max rock height. First clear row. Okay. Index out of bounds. 81. Try push. Print as exp rock in array. Ow. All right, so it's first 2 3 3 3 4 3 5 3 2 3 3 3 4 3 5 3. And then line 81. Max height. X. And what is the width? Array dot length t dot rows int. Index out of bounds. Oh. Pushed rock. All right, well, that solves it. Boom. Three, 1, 2, 7. Got it. Elephants, oh my God. That is a lot of rocks. Okay. I can figure this out. So, there are 5 rocks, and my input is 10,000. Okay. Let's see here. So what I want to do is I basically want to hash. Okay, this is what I can do. I can hash the top I can hash like the top 10 rows. Well, this is, I basically want to hash the top 10 rows, keep track of the index that we are in each of the sequences, track the first time after every rock, update the hash, find when we first repeat the sequences, and then we can run it that many times more. Yeah. Okay. So, but what I'm concerned about is five, 6, 7. If like if you have a long string of things, then like you could end up with, you can drop things down here. Oh, okay. Good. This is good to know. So the 26, perfect. Because this is 4 wide. When you drop 2 of these, they will have to be like, the next thing will be at least here. So the furthest something can drop is, let's go this way. So we do 1, 2, 3, 4, and then we do 1, 2, 3. We drop that, and then we drop this, and then we drop this. 1, 2, 3, 4, 5, 6, 7, and then we drop this. And then the next wide bar could go all the way down here. And so we need to consider basically the sum of the heights of these other ones, which is 12. 3, 3, 4, and 2. So we need to look at the last, let max relevant rows equals 13. And you know what? Let's just make it 15. Really 13, but let's do 15 to be safe. Okay, so now we want index t equals t dot index. Okay. Let module game state equals struct t type t equals top rows rock index int push index int deriving sex compare hash. Okay. Let scene states equals hash table dot create module game state in let scene last. All right, my goal is to be done with this by go for 112. Scene last state equals ref false in, while not scene last state do. let state equals in game state dot top rows equals board dot top rows state board rock index equals loop seek dot index rocks push index equals loop seek dot index pushes hash table dot add equals hash table dot add scene states state equals okay. Oh, let store state equals let height equals let first clear fields equals board dot first row clear row in let cur state equals state in hash table dot add let scene states key cur state data clear row. Leave the table unchanged if the key was present. Equals okay in store state scene last state equals store state let rocks pushed equals ref 0 anchor rocks pushed. Let rocks pushed equals rocks pushed in clear row rocks pushed. print f found repeated state after rocks pushed. And then all I need is this. I think that's used. Board top rows state. Let top rows state equals OCaml for loop. Down. Down. Perfect. Down to. Oh, no. In dot range. Range. This dot range start 0 stop 0. Oh. Max relevant rows. Let y equals t dot first clear row minus stop inclusive list dot map f fun dy equals let y equals y minus dy in if y is less than 0, then 3, 4, 5, 6, 7, else. String dot what do we want to do? We want to do array dot map t dot rows y fun ch occupied, if occupied then else. Array dot to list of car list string dot cat set Wow, that's actually a great little function. Oh, this is a dot. Um, 10. Print end line board dot top row state. Oh, that's why everything is unhappy. And because of that. Okay. Oh, okay, I'm not going to make it at 115. First clear row. Max rocks height. Max rock height. Okay, perfect. So it drops, then it looks like that. Then it goes there, and then there, and then there. After 38 rocks. How is that even possible? After 50 rocks. Wait, 3068. Is that my answer? Okay, perfect. Okay. Let rocks to drop equals in. Okay, let cycle length, let first state, first occurrence equals hash table, find x in scene, states, state in. And it's first clear row, first rocks, num rocks. Let cycle length equals rocks pushed minus num rocks in. Let height delta equals board dot first clear row minus first clear row in. Cycle length height delta length height delta print part 2 rocks pushed. What? First top row. Okay, I guess whatever. Oh. Okay, so the cycle length will be 40, I think. What? Okay, that's definitely surprising. Okay. Let rocks left to drop equals rocks to drop minus rocks pushed. Rocks dropped. Rocks left to drop. Let num cycles equals rocks left to drop divided by cycle length and int dot div, oh no, it doesn't have div mod. Num full cycles. Num full cycles. Let final height equals rocks dropped in final height plus equals final height plus num full cycles times height delta in let remaining cycles, remaining rocks equals rocks left to drop minus num full cycles times cycle length in oh. Let final height equals that. Let current height equals board dot first row clear board in, and then for equals 1 to remaining rocks do oh, this is a crucial thing. Reinitialize rocks and pushes. rocks. Rock cycle. So let final delta equals board dot first clear row board minus current height in. Let final height equals plus final delta partial cycle height, partial cycle height in final height. Dang. Sample answer. My answer. Oh my goodness, I'm so close though. Print height after cycle. Current height after remaining board dot first clear road board. Partial cycle height Okay, I don't understand it. Oh. So I'm 37 off. Which is the length of one cycle. Cycle length is 35. The height delta is 53. Oh, this is not rocks dropped. This is board dot current height. Partial cycle height. Height delta. So this is how many rocks we have to drop. Rocks dropped. I'm not incrementing rocks dropped. That's fine. So we see a duplicate state. And we know how many rocks we dropped at that point. And we know how high it was at that point. So we get the lengths. This is the cycle length. And then we get the height delta. This is how many rocks we have to drop. This is how many rocks we have left to drop. We subtract how many we've dropped. Divide rocks left to drop by the number of by the cycle length to get the number of full cycles. Then we get the remaining rocks, which is rocks left to drop minus the cycles times the cycle length. Oh. This should do it now. Let's go. Oh, that's like the totally wrong button I meant to click. How did I log in? Yeah, okay. We're good. I want to see what the leaderboard was for that, because I think that was like okay. Still not great, but okay. All right, let's talk about it. So we are basically implementing Tetris. We have rocks that fall in a consistent order, and we consistently push things left and right as they're falling. And so this area is 7 things wide. Rocks appear 3 points above the tallest rock. They get pushed and then they fall down. If pushing would push them into something, it doesn't fall down. If it doesn't fall down, it rests there. I create this little thing, this infinite looper. You just give it an array of things, and then it has an index, and you ask for the next thing, and it will just loop around. So that's useful. Then I hard code the dimensions of all of the different pieces in XY coordinates, and then have a rock cycle, which is just the line, the plus, the L, the bar, the box. Parsing the input is pretty straightforward. Convert the less than greater than to left and right. Max rock height is 4, offset is 3. So then we have this board, which is basically a, oh, interesting. That's surprising. Whatever. So we have this board. Crazy. So we have a board, which is all of the rows, an array of booleans, a width. The board knows its width, and then it also knows the first clear row, which starts at 0. First clear row then also indicates the height, rather than the index of the last clear row, which will be height minus 1. So this makes things a little easier. We basically, because like OCaml, or at least the standard library, core Jane Street standard library, doesn't have a vector. So I just figure out like, all right, if this is how many rocks we're dropping, it'll be at least this high, assuming each rock falls directly on top of the one before it. And they're all 4 high. We assume each one will be at least this high, and then that's how big we make our array. And then we make all our rows, which are just everything's initialized to false. And our first clear row is 0. So we have a couple of fun little functions. We have an update coordinates rock, which just, you take in a rock, give it a dx and dy, and we'll change all the coordinates. We use this for initially creating the rock at the correct x coordinate, 2 from the side, and 3 above the top row. Then when we push a rock, we move the X by 1 or -1, and then when we drop a rock, we change the Y -1. Check if there are any collisions, just if any of those positions are true. We place a rock by setting all of those positions to true. Check if it's in bounds. I will call this X inbounds. Check if any of the X coordinates are less than 0 or greater or equal to the width. We try to push a rock, which will return a new rock. Get the direction we're pushing in, update the coords by that dx, and then if it's not in bounds or if there are any collisions, we return the original rock. Otherwise, we return the pushed rock. Try drop, similar thing. If first check if it's at the bottom, then we just return the original rock. This also returns whether or not it actually did drop. So then we drop the rock, updating the coords by -1. If there are any collisions, then we return the rock and say it didn't drop. Otherwise, we did the dropped rock and it did drop. Then we update the first clear row, where we just check if the Y is greater than or equal to the first clear row, we update it. So to drop a rock, we init the rock. We say that it has fallen. And then while it's falling, we try to push it left or right, getting the next push. Then we maybe drop it, and it fell, and see if it fell. So we update the rock with the maybe dropped rock, and then update fell. That ends. Then at the end we place the rock, and we also update the first clear row. And so then for part 1, it's pretty straightforward. We get our pushes, our rocks. We say this is how many rocks we have, create our board, num rocks times, we get the next rock, and then we drop it on the board, and then we print out the first clear row. So then for part 2, for part 1, we just want to know the height after dropping that many rocks. For part 2, we drop 1 billion rocks or 1 trillion rocks. And so basically there's going to be some sort of cycle, and we just figure out the cycle length and then kind of like do the div modding and the remainder and whatever to like skip doing something 1 trillion times. So we need to figure out like what is the state. The state of this dropping thing is which rock we're dropping, which index into this infinite sequence, and also which index into the pushes sequence we are. And then we also need to know like some idea of the top of the stack. So a key thing is that the column is 7 things wide, and the this bar, which shows up every 5 blocks, is 4 wide. And so we know that when the second one falls, it can't somehow get past it. Whereas like you could like pile up all your blocks on one side, and then another block just like falls down along the right side past them all. But eventually we know that it'll hit a rock that was placed 5 times ago. So we know that if we drop a bar here, and then a plus here, and then an L here, and then a vertical bar here, and then a square here, the next horizontal bar could only be down here. So basically this is like how much state we need to consider at any point. There'll never, like, anything below that is totally irrelevant. So that's 13 lines. And so I have this max relevant rows that I just like increase it a little bit. The whole point is it's a cycle, and so it will reappear. Doesn't matter. This just needs to be like greater than 13 or equal. So then I have a game state, which is basically like the indication of the top rows, the rock index, and the push index. So I reinitialize our sequences. I create a hash table of scene game states, create our board. To create a state, let's call this get state. We get the top rows of the board, the index into the rocks, and push the sequences. We say we haven't dropped any rocks, and then when we store the state, we associated with each state, we want to know how many rocks were dropped at that point and the height of the board. Because the key thing is we like know that, okay, eventually at some point, like our tower looks the same after dropping some number of rocks. And then in order to determine what the height of the tower after 1 trillion rocks, we need to know, 1, how much the height of the tower changed while those during that cycle, and then 2, how long that cycle was. And so we store with the state the height basically at the time and how many rocks were dropped at the time. So we say we haven't seen, or actually we store the initial state just to be sure, but that's not really necessary. While we haven't seen the last state, we'll drop a rock, increase the number of rocks we've dropped, and then we store the state and say whether we've seen that. Once we've seen the last state, we get how many rocks were cleared and the height the first time we saw it. We can determine the length of the cycle by subtracting how many rocks we have dropped now from how many rocks were dropped when we first saw it. And we can get the height changed by getting the height now minus the height then. So we have 1 trillion rocks to drop. So we have some number of rocks left to drop. Subtract how many we've already dropped. We'll figure out how many remaining cycles, how many cycles we can do. And then we will, we have some number of remaining rocks to drop. Because we can do the cycle like all the way through, but then like eventually we'll just need to do like 1/3 of the cycle. So we're actually going to like finish off the cycle right away. We drop remaining rocks, and then call this current height. So then the current height is the height after we found the cycle and then dropped enough rocks to like round out the cycle. Then the final height will be that current height plus the number of full cycles times the cycle height. Cycle height. Cycle height. And then that's it. And then we're done. We can get rid of these and this. Yeah. So that was a good problem. They'll like do something a billion times, find the length of a cycle, whatever. Very common advent of code trope. So got that working. Yeah. That is December 17th, 22 solution. Cool.